So we've seen that the energy needed to get to Sydney, we need about 10 to the 8 joules to overcome the rolling resistance, and also about 10 to the 8 joules to overcome wind resistance, drag. So it's about roughly 2 by 10 to the 8, 200 million joules. That's how much it should take to get to Sydney, but how much do cars actually use when going to Sydney? Well, the energy the car actually uses is coming from the petrol. As you worked out earlier, petrol has roughly 3 by 10 to the 7 joules per litre. And if you look up the fuel efficiency figures for modern cars, you'd see that a modern car uses about roughly 7 litres per 100 kilometres. Yeah, some cars are better, some cars are worse, but that would be a typical figure for something like a modern Toyota Corolla. Okay, so Sydney is 300 kilometres, so you're going to need 3 times 7 litres, all times 3 by 10 to the 7 joules per litre, which comes out as about 6 by 10 to the 8 joules. So what we're seeing is that the energy we think it should take to get to Sydney, 2 by 10 to the 8 joules, is about 1/3 of the energy it actually takes for a modern car to get to Sydney. Now if you think about it, that's actually pretty good agreement. I mean, these calculations have had nothing to do with each other. We've had lots of estimates and things. That's actually the same order of magnitude. It's pretty good. What it's telling us right away is that we couldn't get a car more than 3 times as efficient as the current one. Because if it was 3 times as efficient, it would use that much energy, and that's what you just need to overcome wind resistance and rolling resistance. The only way to make it better than that would be to get rid of rolling resistance or wind resistance, something like that. But why is there a gap? Why is it this 3 times less than that? Well, the main factor is that the engine of a car is a heat engine. I don't just mean an engine that gets hot. This is a specific term in physics and engineering and chemistry. It's a machine that turns heat into useful power. In this case, you burn the petrol, making some very hot gas, and you turn that heat into propulsion to Sydney. And it turns out that from the laws of thermodynamics, a heat engine efficiency is always less than or equal to 1 minus T cold over T hot. This is the Carnot efficiency. Now what does this mean here? You can't just turn uniform heat into power. You can't just turn all the heat in a bath into power. You can only turn heat difference. So for example, in a car, you're looking at the heat difference. The heat inside the engine is much hotter than the heat out the end of the exhaust pipe. And it's that heat difference that's giving you power. If the temperature inside was the same as the temperature outside, there'd be no pressure gradient, so you couldn't get any work done. Likewise, if the outside was the same heat as the inside, you wouldn't be able to get any work done and propel anything. So this gives us a limit to the efficiency. Now, let's assume the temperature outside is around 20 Celsius. How hot can it be actually in the cylinders of the car when the explosion's going on? Well, I mean, presumably you want it the hotter the better, because if you make this very large and that very small, this efficiency becomes very, very large. So a temperature of 10 million degrees inside would give you efficiency that's very, very close to 1. However, you can't get away with a heat that high. First of all, the engine would melt. I mean, the melting point of steel is about 1,000 degrees, so T-hot can't be more than 1,000 degrees, unless you make your engine out of some sort of high temperature resistant ceramic, in which case you might get up to 2,000 or 3,000 degrees. But even that won't help you, because what happens is you got your cylinder in the car and you spray petrol in, and then at the correct moment it fires and drives the piston down. But if the temperature is too hot inside, the petrol will explode as soon as it's fired into the cylinder. This is called knocking, and it's a very bad thing for car engines. And that puts the upper limit on how high the temperature can be, which is maybe about 300, 400 degrees, something like that. Any hotter than that and the petrol spontaneously combusts the moment it's sprayed into the cylinder rather than waiting for the correct time. So if we factor in a temperature of about 300 here, We have to bear in mind these are both in Kelvin, so that's 273 degrees is absolute 0 plus 20, and this is 273 plus 300. So that's about 300 over 600 roughly, so that's about a half. So the efficiency is going to be no more than ballpark a half. So you factor that in, that tells us that we need to double this if you're burning petrol to produce it, which is going to be about 4 by 10 to the 8, which is actually pretty damn close to 6 by 10 to the 8. So what it's telling us is that cars are actually fairly close, in this case within 50%, of the theoretical limit. They're burning their energy primarily to overcome wind resistance and rolling resistance, and they're doing about as well as they can given the temperatures of the engines. I mean, you can get engines that run a bit hotter. Diesel engines, for example, run a bit hotter because they don't need to worry about knocking because of the design. The petrol self-combusts in them, and that's why they're more efficient than normal internal combustion engines. But nonetheless, you're not going to get much better than this, and so they're pretty efficient. We might be able to make them 50% more efficient, but we're not going to be able to make them 100 or 1,000% more efficient. So maybe this is the reason why progress in cars has been so slow. They really are already close to a theoretical limit. There's no edge to make them much better. We can make computers 1,000,000 times or 10 million times better, but we're not going to improve the efficiency of cars by more than most a factor of 50% or 2 or something like that without making some more radical changes.